We've been exploring the idea that transition metal ions have colour throughout the course, and this classic example, copper 2 sulfate with the CuH2O6 times 2 plus a blue solution is here. Now, this is a known concentration of copper 2 sulfate, so this is 1 molar concentration, 1 mole per decimetre cube concentration in this bottle. In this bottle, I've got an unknown concentration of copper 2 sulfate, but I think it's a lot less than 1 molar because if you can see, it looks a lot paler in colour. And indeed, as the concentration of a particular chromophore, in this case the transition metal ion in solution, increases, then the depth of colour increases as well. In other words, more light is absorbed in that sample and less light is transmitted through it. And we can use that in order to try to work out the concentration of the unknown in this bottle. In order to do that, we need to use one of these gadgets here, which is called a colorimeter. And so the colorimeter has a light source on this side. Then between the light source and the detector on this side, you place a cuvette, which will have solution in it, like so, and you can measure the absorbance of light that passes through that particular sample. So in order to do that, this is another example of calibration, really. It's important to know what that absorbance reading is for 0 moles per decimetre cubed of the copper 2 plus, so in other words, just using some distilled water. It's important to know what the reading is for 1 mole per decimetre cubed copper 2 sulfate solution. And indeed, it's important to measure some of the values in between the two to check that it's a straight line, or indeed to produce a line of best fit if necessary. So the method of colorimetry works as follows. Take some known concentrations of that particular substance and record the absorbance of those substances, those concentrations, on the colorimeter. Then finally, using the same machine, take a sample of the unknown concentration and record that. Plot the data from this known concentrations so that we have a relationship between the concentration and the absorbance, and then use the graph to work backwards and find out the concentration of the unknown concentration from its measured absorbance. So this is how we do this then. So I'll just take the colorimeter now, and I'll start off with a cuvette and pop some distilled water in this one, like so. So I'll pop a lid on it so that it doesn't spill inside the machine and damage the machine. Turn the machine on. I'll just pop that into here. And I'm going to press the button there and calibrate that so that it's at 0. So for 0 moles per decimetre cubed, the absorbance is 0.00 on that scale. Remove that one. The second one I could do, if I wanted to do, is the copper 2 sulfate. So I'm just going to get a dropping pipette from around the lab so that I can add that to the sample. So I take a dropping pipette, add some of the 1.00 moles per decimetre cube solution to the cuvette like this. Check that there's no air bubbles, that's important, so that there's no scattering of that light. Pop the lid on it, gloves out of the way, and sit that one into the reading. And that's 1.64 for the 1.00 moles per decimetre cube solution. And I can keep going and as I say, measure the various concentrations in between the two. So in a few moments I will make up some known concentrations of that copper sulfate, for instance by taking the volume of the 1 molar and diluting it up to 100 centimetres cubed, testing that one, diluting again quantitatively, testing that one, and so on, so that I've got a good range of values. Whilst I'm here just now, why not do the unknown concentration one as well? I'll take that unknown concentration, I'll take this pipette just to add that into here. So whatever that unknown concentration is, I can measure that it gives an absorbance reading of 0.28 on this scale, so the unknown 0.28. So I will now go away and make some more solutions of this up, quantitatively dilute them, then produce a graph of the concentration, the known concentration against the absorbance that I've measured on here. And finally, I will then use the graph and convert that 0.28 absorbance units back to a concentration term.